In this question, we're going to graph the curve y equals x squared minus 4x plus 1 over x minus 1. Well, when we look at that expression, we see that there's no horizontal asymptote because it's degree 2 over degree 1. There's a vertical asymptote at x equals 1 because that makes the denominator 0 and not the numerator. So since it's degree 2 over degree 1 after simplifying, we're going to have an oblique asymptote. We use synthetic division, and we see that our function is actually equal to y equals x minus 3 minus 2 over x plus 1. So we have an oblique asymptote at y equals x minus 3. Now, some people like to do an analysis on this remaining portion where they say, as x goes to infinity, as x goes to positive infinity, negative 2 over x minus 1 will be a negative number. So as x goes to positive infinity, our y value will approach the oblique asymptote from below. Similarly, as x goes to negative infinity, negative 2 over x minus 1 will be a positive number, meaning that our y value will approach the oblique asymptote from above. Some people like to do that analysis. If you don't do that analysis with the rest of the stuff that we do in this question, you'll be able to still draw an accurate graph. But regardless, we see that we have an oblique asymptote at y equals x minus 3. Now for intercepts, we let x equal 0 and see that y is 1 over negative 1, which is negative 1. So we have a y-intercept at 0, negative 1. And to determine our x-intercepts, we let y equal 0. X squared minus 4x plus 1 equaling 0. Leads us to x equaling 2 plus or minus root 3. So our x-intercepts are at 2 minus root 3, 0, and 2 plus root 3, 0. If we're asked for this information on a test, these are the numbers that we're going to give. But for purposes of graphing, it's good to know that 2 minus root 3 is approximately 0.3, and 2 plus root 3 is approximately 1.7. Now, given this expression for y, we can use the quotient rule to determine the first derivative. And we get this expression, and we can expand out this expression and collect like terms, and we get x squared minus 2x plus 3 over x minus 1 quantity squared. Well, if y prime equals 0, that means the numerator equals 0. Well, if the numerator equals 0, that puts a negative sign underneath that square root. So we see that we actually don't have any point where y prime is 0. There's no point on this curve where the first derivative equal to 0. But y prime is undefined when x equals 1. When x equals 1, the denominator equals 0. So y prime is undefined there. Now, given that y prime is equal to this expression, we can use the quotient rule again and determine an expression for y prime prime. Now, looking at this, in this quantity here, x minus 1 is a factor, and in this quantity here, x minus 1 is a factor. So we can actually factor it out of both of those quantities, and we're left with this quantity in the square bracket. Well, crossing out this factor of x minus 1 with one of the factors of x minus 1 here gets rid of it in the numerator and gives us x minus 1 cubed in the denominator. If we expand all this out, we get this expression, and collecting like terms actually gives us negative 4 in the numerator. So we see that the second derivative never equals 0 because the numerator is negative 4, it's a constant, and it's undefined when x equals 1, and that's no surprise because there's literally no point there. We've got ourselves a vertical asymptote. Now, notice that x squared minus 2x plus 3 is greater than 0 for all x element of the reals. X squared minus 2x plus 3 cannot equal 0. If we set it equal to 0 using the quadratic formula, we'll get a negative value in the discriminant. So since it's a quadratic function that cannot equal 0, it's either always greater than 0 or always less than 0. And if we want to know which one it is, just take any real value of x, plug it in here, and you'll get a value greater than 0. So that means in this instance that this expression is greater than 0 for all real values of x. So now we're going to do our interval testing. We've got the first derivative and second derivative here. So y prime, when I let x be a number to the left of 1, the numerator is positive and the denominator is also positive. When I let x be a number greater than 1, the numerator and denominator are both positive. So I have a function that's increasing to the left of 1 and increasing to the right of 1. Now my second derivative is positive to the left of 1 because I have a negative numerator and a negative denominator, and it's negative to the right of 1 because I have a negative numerator and a positive denominator. So putting all of that together, we see we have a vertical asymptote at x equals 1, an oblique asymptote at y equals x minus 3, a y-intercept at 0, negative 1, and these x-intercepts approximately, with this going on with our first and second derivatives. So we see we've got our intercept at 2 minus root 3 and 2 plus root 3. We've got an intercept at 0, negative 1. We've got a vertical asymptote at x equals 1 and a slant asymptote or oblique asymptote at y equals x minus 3. So we can draw in the function to the best of our ability, respecting the asymptotes. This, it's hard for me to draw quickly, but this should be getting ever closer to that oblique asymptote. As we go to infinity, this curve will get closer to that oblique asymptote. And as we go to negative infinity, this curve will get closer to that asymptote. And same with the vertical asymptotes. And now we can take a look at our chart and see if we have it right. Well, we see that to the left of x equals 1, we're increasing and we're also concave up. In other words, the curve will be above any tangent line that we try to draw. On the other side of x equals 1, we see that we're increasing and we're concave down. We're increasing, but the curve will be below any tangent line that we try to draw. So this is actually a good graph of the function we were asked to graph.